Welcome back to the deep dive. Today we are going to try and do something. Well, something impossible. We are taking the chaos of the world,
All of it.
all of it, the millions of things that all depend on all the other things, and we are forcing it into a straight line.
That really is the ultimate goal, isn't it? And it's surprisingly difficult to do, mathematically
It
speaking.
is.
The sources our listener handed us are just fascinating. They detail the algorithmic principles. It's like a secret language, really, that can transform this scheduling nightmare into a clean, linear, executable order.
And the mission here, it really boils down to a problem of scale. You, our listener, you asked us, how do these massive interconnected systems, I mean, we could be talking about designing a microchip or, building an entire city block, how do they manage millions of interdependent tasks
Without just failing.
without totally freezing up or just getting hopelessly stuck in a loop of waiting for each other?
It's the essential question of modern engineering, really. Every single task is constrained by the ones that came before it. And the language we use to tame that web of constraints is the directed graph.
Okay, so let's establish the map for everyone. In this model, this mathematical map, the tasks themselves, the actual things that need to get done, those are the vertices.
The points on the map.
Exactly.
8 points on the map.
And the rules, the you can't do this until that is done
Mhm.
part, those are the arcs, the arrows. They show you the exact path of dependencies.
And once you draw that map, the goal becomes really, really clear,
It does. It becomes all about topological sorting.
which is a fancy way of saying putting everything in the perfect order.
It is, yeah. It's this elegant procedure of arranging every single vertex so that all of its prerequisites are met before that task actually starts. It creates this crystal clear linear sequence from start to finish.
And this is where, I guess, one of computer science's most foundational ideas comes into play.
One of those elegant, for sure. Okay, so let's unpack this. We should start with the problem itself, what the sources called the circular situation. The analogy they used, which I thought was perfect, was building a house.
Right. The easy parts are, well, easy. You pour the foundation, then you build the walls, then you put on the roof. It's a simple sequence.
A to B to C, no problem.
That's a straightforward one-way dependency. But the chaos starts when the teams have to interact. That's where you get these tight loops.
And the plumbing team and the electrical team.
Exactly. They often need to get into the same walls at basically the same time. The plumber might need the electrician to roughen a wire before the pipes go in.
But the electrician needs the plumber to move a vent pipe before they can run their main line.
And there it is. They're locked in this mutual dependency dance. If you try to force them into a strict order, plumbing is 100% done, then electrical starts, the entire project just stalls.
Because they're just sitting there waiting on each other.
That tight loop is the fundamental barrier to a simple schedule. And in graph theory, we have a name for that lockup.
Strong components.
Mhm.
Or SECs.
Yes. An SEC is basically a group of tasks where you can start at any one task, follow the arrows through other tasks in the group, and end up right back where you started.
It's the literal definition of a cycle. You're just going in circles.
You are. And if you're a scheduler looking at that on your dependency map, the graph is screaming at you. There's no simple sequential path through here.
So the algorithm's first job isn't even to create an order. It's to find and eliminate those cycles.
What's in the way it does that is,
Huh.
well, it's a brilliant bit of compression. It's almost like mathematical alchemy. The algorithm finds these strong components, these chaotic loops, and it shrinks them.
Shrinks them.
It shrinks them into a single unified point. We call it a super vertex.
So you basically just stop worrying about the internal back and forth between the plumbers and the electricians for a moment,
Right.
and you just treat that entire mess as one giant task called, I don't know, rough-in systems complete.
That is precisely the practical implication. Once you shrink all those messy components down, your entire dependency map transforms. It becomes what we need for ordering a directed acyclic graph.
A DAG.
A DAG. And the key word there is acyclic.
Meaning no more cycles.
No more cycles. You've simplified the entire universe of tasks. The path forward is suddenly visible.
This is where it gets really interesting, because now we can move from the theory to the actual mechanism. The tool that does all this finds the loops, shrinks them, is Tarjan's algorithm.
Robert Tarjan. His
Yeah.
work is just legendary. And what makes this algorithm so critical, even 50 years later, is its incredible efficiency. It doesn't just find the strong components.
Right, does more.
It simultaneously produces the topological sort of those components. It finds the chaos and delivers the ordered timeline blocks in one single elegant pass.
The sources describe it as being like a spelunker exploring a cave. It uses what's called depth first search, or DFS.
Right, it goes deep. It follows one path of dependencies all the way to the end, and as it goes, it classifies every single connection, every arc it finds.
And that classification is how it finds the loops.
It's vital. As it explores, it's defining arcs as tree arcs, cross arcs, forward arcs, and crucially, back arcs.
Okay, so what's so important about a back arc? Why does that matter to the person trying to build the schedule?
A back arc is the problem we're trying to solve. It's an arrow on the map that points from where you are back up the path you just came down.
So if the electrician's task points back to a task the plumber started.
Boom, that's your back arc. It closes the loop. It is the mathematical proof that a strong component exists right there.
And this is the elegance that led the great Donald Knuth back in 1973 to call this the algorithm I love best. He said it taught him something fundamental.
A huge lesson, yeah. That data structures themselves can also be deep.
What did he mean by that?
Well, back then, a lot of people in the field thought of data structures, arrays, lists as just simple containers for storage.
Just buckets to hold numbers.
Right. Exactly. But Knuth realized that Tarjan had engineered a structure, specifically the way he used a simple stack, that was intrinsically part of the discovery process. It wasn't just holding data, it was finding the answer. That was a huge shift in thinking.
And that ingenuity was necessary because of what the sources call the circular problem paradox.
Yes, this was a real chicken and egg problem. The paradox was this. To identify the boundaries of a strong component, you need to know this value called the low point.
Okay.
But to accurately calculate that low point, you first needed to have already identified the components. It seemed impossible.
So how did Tarjan solve that? How do you thread that needle?
Tarjan's secret sauce was, it's almost deceptively simple. He solved it using just two things working together, a single stack.
Just a list of things you've seen.
Just a list of the nodes, the tasks visited in order, that plus a low point value that was maintained for every single vertex.
So as the algorithm is exploring this dependency cave, it's pushing tasks onto the stack. What is the low point telling it?
The low point is like a memory. It tracks the index of the highest, oldest ancestor that the current task can reach, often by following one of those back arcs we just talked about.
So if you hit a back arc, the low point value updates.
It updates to point to the root of that cycle. So it's not just tracking what you've seen, it's tracking the furthest point back that the current path is connected to.
I see.
And here's the genius of it. The low point lets the algorithm know the exact moment, the exact nanosecond. An entire strong component has been fully explored.
How does it know?
When the low point of a vertex equals its own initial index, the number it got when the search first found it, that's the signal. It means that vertex is the root of an SCC.
It's the entry point to the side.
It's the entry point, and everything below it on the stack that hasn't been assigned to another component yet belongs to this one.
So that's the trigger that says loop closed, component complete.
That's the trigger. And at that precise moment, the algorithm can just pop the entire component off the stack at once, confirming completion and giving you that nice, clean super vertex. The stack isn't just a bucket anymore.
It's part of the engine.
It's an active part of the discovery. That's the deep data structure Knuth was talking about.
And the sources contrast this with other approaches at the time.
Oh, absolutely. Tarjan's is all about elegant simplicity. One stack, one extra number. Dijkstra, who was another giant in the field, developed a solution that was more like structured complexity. It required managing 4 different new arrays just to keep track of the state of the graph. It worked, of course. But Tarjan's minimalist approach is what became foundational. It's the difference between a sleek sports car and, a giant complex machine that gets the same job done.
Okay, so we've resolved the internal chaos. We've shrunk those plumbing and electrical conflicts into our super vertices. We now have a topological sort, but that only gives us a partial order, right?
That's a crucial distinction, yes.
It gives us ordered blocks, but not the final minute-by-minute master schedule.
Exactly. The topological sort of the strong components tells you that block W1 has to happen before block W2. But if you want that complete, binding, total linear order,
The master
the
schedule.
master schedule, we need to talk about weak components.
Weak components. They sound a little less problematic than strong components. What are they doing?
They're arranging those already shrunk supervertices, those strong components, onto a straight line. W1, then W2, then W3. They give structure to the overall timeline.
But there has to be some kind of strict rule, a mathematical condition that says, yes, W1 can be strictly followed by W2, or no, these two have to be merged together.
There is, and it's incredibly elegant. For component Wi to be strictly followed by Wi plus 1, the condition is this. Every sync vertex in Wi.
A sync being a task that's a dead end with no further requirements inside its own group.
Correct. Every one of those syncs must have an arc, a connection, to every source vertex in the next component, Wi plus 1.
A source being a task that starts things off in the next group.
Exactly. So let's go back to the job site. W1 is our rough-in systems block, and let's say it has 3 final finishing tasks. Those are the syncs.
Okay.
And W2 is insulation and drywall, and it has 5 starting tasks. Those are the sources.
So 3 syncs in the first block, 5 sources in the next.
To have a strict, clean handoff, you must have 15 dependency arcs, 3 times 5. Every single one of those syncs has to connect to every single one of those sources.
And if even one of those 15 connections is missing,
the strict sequencing fails because you can't guarantee a clean handoff. Some part of the drywall work might inadvertently start before every single part of the rough-in is truly complete.
that makes perfect sense. If that condition fails, the blocks have to merge.
They have to merge. And this logic is just invaluable for schedulers. It tells them exactly which tasks must be bundled together and managed as one big unit versus which can be neatly sequenced end to end.
This is really the foundation of how these huge scheduling systems work. Which brings us to scale. We're using algorithms from the 1970s to manage dependency trees that have millions of nodes today.
The efficiency isn't just a nice to have, it's existential. If your scheduling software takes longer to run than the actual project, well, it's useless. And this brings the story right up to today.
Post-mature optimization. I love this idea.
That's fascinating.
The concept that a 50-year-old classic, totally mature solution can still be refined to squeeze out more performance.
It really is a testament to that depth Knuth was talking about. Knuth and Tarjan collaborated again in 2022 to do just this. On modern problems with millions of tasks, they found a way to reduce the memory accesses the algorithm needed from about 7 million down to 5 million.
Which might not sound like a lot in an age of terabytes, but when you're running these calculations over and over in real time,
It's massive. That's a huge savings in computational speed and power. They did it by redefining the low point calculation a bit and combining some data fields. It just proves that these classic algorithms aren't museum pieces.
they're living documents.
They're living documents, exactly, open to new insights.
And Knuth also noted that his recent work is focused on constraint satisfaction.
Which is deeply linked to scheduling. Constraint satisfaction is all about finding a solution that meets a whole set of specific requirements, fitting a million tasks into a fixed deadline with limited resources. These graph algorithms are the engine that makes solving those huge problems possible.
So this brings us back to the real-world applications for you, the listener. It's not just about project scheduling for construction or software. This stuff is absolutely central to designing VLSI chips.
A perfect high-stakes example. The sources talk about clock skew scheduling. You can think of the pathways on a microchip as an impossibly complex subway map.
And the electrical signals are the trains, moving at nearly the speed of light.
Precisely. And every train, every signal, has to arrive at its station at the exact right moment to avoid a timing failure, a collision.
So if you fail to resolve a strong component in that chip's design, a dependency loop,
You've created a race condition. You've basically guaranteed a collision on your subway map, and that leads to chip failure.
so the ability to find those secure dependencies and compress them is what keeps our entire modern computing world running on time. Whether you're building a house or a new processor, the math is the same.
We've really seen how Tarjan's elegant method identifying these strong components, these crippling loops, using just the simple mechanism of a low point and single stack, creates the topological sort that turns chaos into a linear plan. It's the invisible, efficient foundation for the largest scheduling systems in the world.
It's an absolutely remarkable story of human ingenuity meeting pure complexity. And at the end of the day, the sources reveal that this story is really a testament to the search for elegance in computer science.
It is. So the question for you to think about is this. If such a seemingly simple pair of concepts, a single stack and a tracking number, can organize the construction of microchips in entire cities, what other simple overlooked concepts might be secretly holding together some of the world's most complex systems right now without us even realizing it? Something to mull over as you organize your own dependencies.